also be used in misleading ways. And what we're saying is, don't mislead the public. I mean, that's a no-brainer, right? You should realize that you should mislead the public and be dishonest. But particularly at this moment, don't use these tools nor allow them to be used.
It can be quite a fine line. Everyone would say they don't mislead the public, but there's a lot of creativity in campaigning, and as the stakes get high close to an election, there's, you know, there might be things that are quotes put out of context, you know, images of people looking particularly, well, I mean, you know, remember Ed Miliband eating the bacon sandwich? It was not flattering, but it was a real image.
Absolutely. But if generative AI is used to create any images that might be satirical, that's a great traditional kind of part of political campaign, just label it. Just be open, transparent, and truthful about it.
So an actual caption on any image, do you?
Yeah, definitely. I mean, it seems no problem to do that. It's very easy to say, you know, we used AI to generate a funny meme. Why not?
Yeah. But then, so what, Polly, would you say? So there's no issue with actually creating it. Then you wouldn't have a problem with, say, the Labour Party using a deep fake voice of Rishi Sunak, as long as they put some kind of message on it?
We've put together a draft agreement that's oven ready if they want to use it. It says don't create deep fakes, don't purport that someone said something they didn't say, but if you do for kind of satirical reasons or at the kind of creative kind of edge of this, just label it, just be really open and transparent. So we're not saying that it might not be acceptable to use at points in
the labelling.
That's for the parties to come together and agree. But if you think about any, so
this is a fake
by no, just produced using a particular tool, like we label pictures from particular photo agencies, for example.
I mean, that could be quite subtle and probably not get to the heart of the fact that it is a fake, Jimmy.
Yeah, and I think that we would all say this is only the most minimal step that parties can take, is to agree not to do this. There's a lot more that can be done in the future. There's a lot that social media companies should be doing to work on this. I think there's a lot of ways we should be thinking about legislation, but that's for the future. We don't have time for that right now. It's a simple thing that all the parties can do today.
Jamie Wells, founder of Wikipedia, and Polly Curtis, chief executive of the think tank Demos. Thank you both.
Only last night one of my children was playing me someone else's birthday messages from President Obama and President Trump. They were not, of course, but boy, they sounded as if they were. And that's all from us today. Our editors were Hannah Wilkinson and Tom Smithard. The studio director was Lee Wilson. Have a really good day.
BBC News at 9 o'clock. There's a growing expectation that Scotland's First Minister, Hunter Youssef, could resign as early as today, rather than face 2 votes of no confidence. Sources have told BBC News he's considering stepping down because he doesn't think he has enough support to win the votes. Mr Youssef is leading a minority SNP government after he suddenly ended a power-sharing deal with the Scottish Greens. Our political editor, Chris Mason, is following developments.
He has sustained huge political damage in the last couple of days. I would not be surprised if the First Minister has gone by lunchtime, facing a situation where the better option is to quit, to go broadly on your own terms, or at least jump before you are pushed by those numbers that simply do not lie.
MPs will this afternoon debate whether assisted dying should be legalised for people who are terminally ill. The debate was triggered by Dame Esther Ranson through a public petition signed by 200,000 people. She told Today the aim was to offer a pain-free, dignified death. Opponents, though, argue that vulnerable people could feel undue pressure to end their lives. British and Irish ministers had to hold talks to tackle a growing row about migrants. The Irish government says there's been an influx of asylum seekers crossing from Northern Ireland because they're fearful of being sent to Rwanda. The Work and Pensions Secretary, Mel Stride, has said a grown-up conversation is needed about disability benefits after a big increase in the number of people claiming personal independence payments. He said there was a concern that some people were labelled as having mental health problems when they were actually enduring the normal ups and downs of life. The disability charity Scope called the proposed changes reckless. And new laws have come into force to try to stop hackers accessing smart products like baby monitors and doorbells. They ban the use of default passwords such as 1234. BBC News.
This is BBC Radio 4, where as part of a series of programmes about what it's like to be a boy growing up in 2024, at lunchtime all this week we'll be hearing from teenagers around the country, sharing their thoughts and experiences in their own words. About the Boys begins today at 1:45. And the person behind the project is Catherine Carr, herself a mother of teenage sons, and she'll be sharing more about what prompted her to make the series on Women's Hour. That's at 10 o'clock this morning. Now though on Radio 4, it's time for Start the Week with Tom Sutcliffe.
Hello. Prepare for a certain amount of existential vertigo today because we are ranging across the cosmos from the outer edges of the observable universe to particles we're still not sure that they exist that would be billions and billions of times lighter than electrons. The magnitudes and dimensions involved seriously test the powers of human intuition, mine certainly, but our guests today work with them daily. Lisa Kaltenegger is the founding director of Cornell University's Carl Sagan Institute to Search for Life in the Cosmos, and she's just written a book, Alien Earths, about her work looking for clues to the existence of alien ways of being alive. Claudia Duran, Professor of Theoretical Physics at Imperial College London, works on one of the great remaining mysteries of physics, gravity, and she charts her lifelong fascination with the subject in her book, The Beauty of Falling. And Professor Mark Fromhold, Head of Physics at Nottingham University, is with us too, to talk about the exciting ways in which abstract theory and practical application can come together. Lisa, we're going to be talking about huge timescales in this programme, 13.8 billion years since the Big Bang. But I wanted to start with something much more recent. Last Friday, the James Webb Space Telescope spent 8 hours, I think, looking at a planet called K2-18b. 124 light years away, kind of circling a red star. Why are they doing that, and why is it a big deal?
The big deal is that for the first time in human history, we have a telescope that can look at small worlds. So we're not talking about puffy Jupiters that are hot and gaseous, and figure out what's in the air. And that's incredibly hard to do, even with the biggest telescope we have, the James Webb Space Telescope. But we are learning to read what the chemical makeup of the atmosphere of other worlds are, and especially that one is one of the smaller ones. So people are starting to get very excited to see the first hints.
So when you say smaller, do you mean in terms of Earth size? I mean roughly Earth size, twice?
We are still talking above Earth size, but we're basically inching towards Earth size in, for example, the TRAPPIST-1 system. That's another system that the James Webb Space Telescope looks at. But there are a couple of intermediate ones that are just bigger, and we hope that they're rocky. They might also be small gas balls. And so studying those, because they don't exist in our system, they're none of our planets, is really fascinating because we really don't know what they should be like, and so we're finding mystery after mystery, and one being Kepler K2-18b.
Yes, I mean, you do think they could come up with catchier names, but I suppose there are a lot of exoplanets now. I mean,
we found more than 5,600, and there are more than 10,000 candidates that we're still vetting to make sure.
You say we found 5,000. That is recently, isn't it? That's since 1995.
That's since 1995, and so think about it. Every second day on average, we found a new world circling another star. Isn't that amazing?
It is amazing. Was it amazing to scientists? Had they hypothesized that every star would have a planet, or had they thought that planets were rare?
You could do either. Whatever you read. So some people said, oh, it could be 1 in a million or 1 in a billion, and some people said, oh, it should be everywhere. This is where scientific discovery is so much fun, because you have this wide range, and then you measure it and you
before we go on to talk about your work, looking for new worlds and thinking of ways in which you can then detect whether there is life there or not, could you explain 2 terms, because they're relevant here? The first is the Fermi paradox, which I think is coined in that way. Enrico Fermi coined in 1950. What is the Fermi paradox?
So the Fermi paradox basically asks, so if there's so many possible worlds out there,
Where is it now? And I think this is a very natural question. And there are a lot of worries about say that civilizations can survive, and forming of course was working on
Where is everyone? Meaning we should have heard from intelligent life.
exactly, and there are the funny things that questioning is we are kind of assuming that everybody want to come to us immediately if they could just spot us. And so in
I thought that was a very nice detail. We may just have a little dog.
I love the Earth. Let me just say it's my favorite planet because that's the next thing that comes up. But I love the Earth.
But also, because when you look into deep space, you're looking back into time, the same thing would be true in the reverse. They might be seeing this planet as a completely different period of our own evolution.
This is the interesting thing about the speed limit of light. Because light needs time to travel like a car. And so if something is 4 light years away from us, that's the next star over, Proxima Centauri, then we see the star like it was 4 years ago, and the reverse would be true. So think about 100,000 light years away from us. Would you really come and say, hello, I want to come and see the grass grow on this planet?
The second term I wanted you to explain was the Drake equation, because that has sort of changed radically in many ways. What is the Drake equation?
So the question was, what do you need to know to figure out how many civilizations should be out there? And Frank Drake was an amazing American scientist who put this into a formulaic way of thinking. And so he said, first you need to know how many stars there are, how many of those make planets, how many of those planets could make life, intelligent life, and communication. And so basically, we know how many planets there are, what's amazing because we solved half of it. And if we were to find signs of life on another world, we could solve the other half.
A lot of those terms in the Drake equation were highly speculative. You could come up with pretty much any number, but some of them have been narrowed down a bit, haven't they? I mean, the James Webb has revealed that you shift towards one end in your guesses about the number of planets there are.
Absolutely. So these different missions, Kepler from NASA was looking at how many planets are out there. We figured out that 1 out of 5 stars have a planet that could be like ours. So with 200 billion stars in our Milky Way alone, our galaxy, we have billions of possibilities. And this is why we live in this golden era of exploration, and with the James Webb for the first time we can actually look and explore the light of these worlds.
The question is what we're looking for. Can we address what we mean by life? Is there a paradox that our search for alien life will necessarily be a search for life as it is familiar to us, whether it's microbes or primates going into space? So in a sense, we're not looking for alien life, we're looking for life like us. Are we not?
We're definitely looking for life like it was here on the Earth, so carbon-based, water-based, and the scaffolding of carbon, solvent, or water is our best guess right now, and we also keep our eyes open for any weird signals. But we do know that life at least once used carbon and water.
So you haven't ruled out the possibility that there may be a form of life that kind of has a completely different basis for existence?
Absolutely.
And if we saw its signs, we would certainly not initially at least recognize it as life.
That's the problem, because if we could make life in the lab here on Earth, then we could mix the chemistry differently and tell you how different life would look like, what it would breathe, because I'm really looking at gases or on the color of planets out there. But as long as I don't know, weird signals it is, in addition to what I know to look for.
Tell us about your work, because at one point in your book you say, what is an astronomer doing in a biology lab growing microorganisms? What's the answer to that?
Well, the astronomer figured out that we do not know what life, if it's not green plants, in all these different beautiful colors would look like. And so then the astronomer decided that they had to reach out to their colleagues to grow as much diverse life as humanly possible, to just not miss signs of life out there, because we don't want to be too narrow-minded.
So you're creating a kind of paint chart of the colours of life.
Absolutely, a color catalog of life, or the have a lot of biopigments and activity of this diverse set of life of the Earth, especially also through time. Because think about it, if we just saw it from a little bit younger or older than ours, we don't want to miss the sense of what it's out there.
The gases are important too. That, as I started with the James Webb Telescope on Friday, was looking for. Why was it looking for that in particular, black gas? And what does that say?
So the key point is there are some gases that can be made by life or by geology, and then there are some gases that we only have explanation for. What we currently are doing is the dimethyl sulfur. It could be life, it could also be not life. So, but it's easier to bigger worlds that you were talking about, like on Friday. So we have the first hints that there might be a wiggle in the spectrum, and that's of course very exciting. But we still have to get more data to beat down the noise, because we're making these measurements and there's a star involved that changes next to the planet before we can be sure what we see.
You raised the idea several times in your book that, of course, if we can look out into space, something can look back. If an alien intelligence was looking in our direction from those same distances, what would they see that would sort of set up a red flag, if they have red flags wherever they are?
So the golden fingerprint of life that we deduced from the Earth with the combination of oxygen and reducing gas like methane, just because it reacts to CO2 and water really fast, so seeing it at the same time in the atmosphere, we have no other explanation than for this to be life. So that's really what we're going towards, but it's so hard to find. And the fun thing is, with all this research, is you sit there, and at one point I was asking myself, hey, if there were alien life out there, and if they just had our level of technology, where would we be the aliens?
Claudia Ram, I was interested. One of the advances made was gravitational, wasn't it? That we were able to observe around very distant stars tiny perturbations in the star, which suggested there was something of mass next to it.
Absolutely. So when two objects are going around each other, they exert a gravitational pull on each other. And then you mentioned about the wobbling stars, that in looking at its motion, you know that it's not alone. And we understand that very well. So it's beautiful to see these different fields of research really aligning. And nowadays we're using very much different channels of communications to understand everything around us, from gravity to light.
Does that wobble tell us about the nature of the planet that's circling the star? Can it tell us whether it's a gas planet or a rocky planet?
It will tell us about the mass.
Oh, right,
star.
only the mass,
That's
and
right.
so you don't know what it's composed of necessarily.
Yes, and the distance probably, and how they interact, but very much about the gravitational interaction between them, but not the composition per se.
Mark Fromholt, you teach physics.
Yes.
Do these questions come up? Is it part of the kind of glamour of physics?
It should do. I mean, it's often something that is talked about in tutorials, for example. You know, certainly colleagues will look at what's topical, what's coming up. Recent discoveries, and weave that into tutorials. In lectures, we draw on our research all the time, and other people's research as well, to make things relevant so that students can see that what we're teaching is relevant to their lives and also to their futures from the point of view of careers and making socio-economic advances through those careers.
Before I move on to Claudia and gravity, can I just ask, can we see any of these planets? Have we taken pictures, as it were, that we can see? Not through infrared, but in visible light to us.
We see the shadow of those planets when they actually block out part of the hot stellar surface. So if shadows are okay, we have seen a lot, but we also have the first snapshots of a couple of these very young, hot, big worlds around their star. And like a baby picture, they will actually fade from view because it's big and hot, but we're getting better at this. So we're getting to see more of them, and then we could catch their light. Because right now we see the light of the star filtered through the atmosphere coming towards us. But if we could see it kind of just like a pale blue dot, we could see what it's made out of.
Do you have a kind of particular favourite exoplanet? I mean, are there exoplanets that you are particularly concerned in their study?
Absolutely. So the TRAPPIST-1 system, a red sun with 7 Earth-sized planets, and 3 of them in this Goldilocks zone, not too hot, not too cold. It's one of my favorite systems, and we're using the James Webb right now to actually analyze it, to identify gases, and it's such a hard measurement, I can't even tell you, but we're working on it all together internationally to figure this out.
Do they have names, those planets, or are they're all strings of names, names and numbers?
Absolutely, going back to what you said before, the romantic names of TRAPPIST-1A, well, TRAPPIST-1B, we start with B, B, C, D, E, F, G, H, just has such a beautiful ring to it. But the problem is, like, if you say, let's do some names of heroes or gods, right? You run out of them because we have 15,000 planets that we need to name.
And we're discovering about
but
one a day.
Everybody can actually name. If you go online, you can actually name your own worlds, and this is why at the end of the book I have a couple of links. So name your own world and help us not call them numbers.
I want to turn to what's keeping those planets in place and what's keeping them in the cosmos, which is gravity. Claudia Laurent, I wanted to ask you a couple of simple questions about gravity first. That just may get us through the door of how strange it is. Is it a strong force or a weak one? I mean, we experience it as, particularly at the end of the day, going up the stairs pretty strong. But a child can break the link of an entire planet briefly by jumping in the air.
That's right, it's incredible. One of the tricks I love for birthday parties or anything you want, if you rub a balloon on your hair, then there's an exchange of a few electrons between those of your hair and the balloon, and then you see that the static is from the electron which is sufficient to pull your hair in the air and you pull the balloon away. And so you imagine just a few electrons are sufficient to counteract the whole gravitational attraction from the whole Earth. Can you imagine that? It's incredible. So gravity, we feel it, and we do feel stronger when we hit the ground. Down the stairs, for instance, but in itself, it's the weakest phenomenon that we have ever experienced. It's incredible.
So it only has this force on us as individual humans because it is the entire planet that is exerting that force.
That's right.
Now, I understand that the Earth exerts a gravitational pull on me. Do I exert a gravitational pull on the Earth?
You do, not only on the Earth, but on us right now. You are attracting us.
You say in your book, I mean, and it was one of the kind of startling facts, that objects at the very opposite ends of the universe exert a gravitational pull on each other. Now, presumably that is a tiny.
It does get diluted away as a function of the distance. So the further away you are, of course, the weakest the gravitational attraction will be. And Newton was the first one to very much express that in more mathematical terms, understanding how fast it gets diluted away. But technically, it's still there. It never really dies out.
So there is no point at which it diminishes. Is that the same? Is the same true with light? Do we eventually arrive at a point where light does run out?
It is the same phenomenon with light or with the electromagnetic attraction or repulsion with the same force. But it's not true with every forces in nature. And actually, the electromagnetic force and gravitational force are like that. And that's probably why we are more used to them, because they never really switch off, unlike the other forces that we're less comfortable with.
Newton obviously made an early advance in understanding how gravity operated on objects.
That's right.
Did he have problems with the notion of this universal force that was working on everything at once, sort of instantaneously?
Yes, so there's two things where he understood that there must be something more fundamental related to the Newton gravitational attraction. The first one is this notion of universality. Him and Galileo and many other physicists at the time have realized this notion of universality, that gravity is unlike any other forces, that it operates on everything and everyone in sort of a universal way. And that's part of what we call the equivalence principle. That's something really remarkable. which tells us that there must be something much deeper related to gravity. It's not just about two masses attracting each other. It must be encoded in something much deeper than that, if it's omnipresent everywhere to everyone. The other thing that Newton realized himself and really couldn't make sense of, he realized that there was some level of instantaneity in the way gravity was communicated. We typically don't think of the speed of gravity or the communication of gravity, but it has to be there somehow.
Because one thing must know in some way that another thing is there.
Yeah, how do we know about the Earth being there when we fall down the stairs? How do we know that we need? How does the Earth know that there is the Sun in the center of the solar system, and we're gravitationally attracted to it? And what would happen if all of a sudden some alien lights came and switched off the Sun, took the Sun away? It would take some time for us here on Earth to realize that. And according to Newton and gravity, universal law of gravitation, there is no notion of communication and time dependence on how this gets communicated to one another. So he knew that there must have been something deeper than that as well.
Now, I understood that Einstein kind of resolved that slightly by saying gravity is not a force, it's a landscape in which we kind of live.
Yeah, I like that term. I like the landscape. I like the...
So that it shapes where we can go and kind of, well, how the universe is around us.
That's right. Both of those things he resolved in realizing that it's not so much about us, it's about where we are in space and time. And the notion of gravity is actually encoded in the very fabric, in that landscape of space and time unified together. That's a lot to take in one piece, but nowadays we understand this to be true to such a fundamental level. And so we can understand that, for instance, planets or stars, through their mass, but not only their mass, through their energies, through everything that made them alive in some sense, live in that space-time, curve the very fabric of space and time around themselves. And we're all experiencing this space-time, we're all in there, and that's how we actually experience the gravitational pull from the Sun or from the Earth. But not only that, this fabric, this landscape, is not something dull. It has a life in itself, if you want. It has a dynamics, and it's through these dynamics of this fabric of space-time that gravity gets communicated. So it can evolve in time as well.
You use the term glide,
which is
light with G on the front of it. What is glide?
I like glide. The real technical term, my colleagues would not approve of that.
Well, you've written a book for a general reader,
so I like to provoke them. Really, it is gravitational waves, but I found that such a technical term. It is correct. It is a wave. Just like light is electromagnetic waves, and you discuss about that. Light is an electromagnetic wave, but we were very familiar with light, and we do observe it on a daily life. So light is the way the electromagnetic force gets communicated, if you want it. It's a messenger for this fundamental force. And just like there is a messenger for this fundamental force, the electromagnetic one, there is one for gravity. And that one is glide for gravity.
Okay, and does glide, so light consists of photons and particles.
That's right.
Is there a particle for glide?
There must be. I would be quite provocative and say, there must be. If there isn't, and we have the quantum physicists there, if there isn't, our whole understanding of how quantum physics works, and we know that gravity connects everything and everyone, including all the quantum world. Every quantum element, like electrons, are connected also through gravity. And so it simply would not make sense. And I know some of my colleagues would disagree.
Well, I'm going to ask Mark Cromwell. You are able to tell me how daring that statement is in scientific terms. I mean, how many people are upset, and how many people are beginning to think, oh, them
50-50. I mean, you would imagine that some scientists get upset quite easily. They're probably upset now and frothing at the mouth a little bit. Others would be a bit more accepting and would actually say, well, maybe that's true. Maybe there are particles of gravity. And my personal view is that there must be, just from the symmetry of all of the other forces that we know about.
Has that shifted? We're talking a lot here about sort of recent discoveries. Has that shifted recently? that 50-50 percentage split?
I would imagine so, yes. I mean, the discovery of gravitational waves was such a huge breakthrough, really one of the massive breakthroughs this century, and people have started to think about waves mediating gravity, and the natural conclusion, you mentioned that photons are kind of the particles of light. The natural conclusion is that in order for there to be symmetry in nature, there must be particles, which are the analogues, the kind of quantum analogues of these gravitational waves.
Claudia, can you tell us what a gravitational wave is, and why was that disruptive to the pre-existing model? I mean, people obviously thought they were there because they built extremely expensive pieces of equipment to look for them, but why was it disrupting the previous model?
So I think, just to illustrate how disruptive it is, we can just show Einstein himself. He came up with the notion of gravitational waves, that in that fabric of space-time there can be ripples. And so when two, for instance, stars or two very massive objects orbit each other, about to merge, they disrupt this very structure of space-time, and that disruption then propagates through waves in space and time. But Einstein came up with that idea, and then himself thought at some point that they must just be an illusion. They must just be a way we parameterize our space-time, but with no physical meaning, with no way to actually observe them.
And how do we observe them? Because I would have thought if there is a ripple in space-time, your experimental equipment exists in space-time, so that it ripples exactly in synchrony with the thing it's trying to measure. So how do you measure?
Yeah, so what that wave does actually is stretches and space between anything, between you and me, as a gravitational wave.
So like a lump, like fruit in a lump of jelly. It sort of stretches.
Exactly. It stretches the very fabric of space and time. It stretches and contracts it in regular interval as the wave passes through. And so if you imagine a gravitational wave were to pass through this room, and well, of course, there would be the vacuum in this room, let's just imagine that, then the space between you and me would be stretched and contracted ever so slightly.
And would it be stretched only in one direction? Is that how you discover?
So it's in two directions, in phase in two different directions. And nowadays, so we have, for instance, ground-based interferometers, the LIGO, Kygra, Virgo interferometers, which are located in different places throughout the planet. And as the gravitational wave passes through, we see that disruption in space, which is simultaneous in those different places on the planet.
So you know it's not a passing car or
that's
a
right.
heavy footfall
That's right.
Yeah. Did I understand you right in saying that when you're talking about gravitons and the possibility of gravitons, that the experimental equipment for that would require you to have a neutron star in the laboratory, to have shielding walls so dense that they would create their own black hole? Is this a theory that is ever likely to be subject to experimental proof?
That's an amazing question, and how can something be true scientifically if we can never observe it? That's a fundamental question. There's different ways we can try to detect a graviton. And we know that if we want to think of a graviton as the fundamental constituent of gravitational waves, of light, and we wanted to look at the effect of just one single graviton through our interferometers here on Earth, the precision we would need is not only technically challenging, it goes beyond Heisenberg's uncertainty principle. So it's even theoretically impossible. And I'm a theorist, so I'm happy to imagine experiments which are as big as the universe itself. I don't have the funding for that.
But even that isn't possible.
Even that is not possible, because the gravitational waves that we have detected here on Earth, they're not just one single graviton. They are 10 to the 44. So that's billions of billions of billions of billions of more than that of gravitons together, in harmony together. They go through our instruments, and it's really team working together. They manage to change the distance between two mirrors in our interferometers by a distance which is less than that of a proton. Can you imagine? So a single one of them, that's just impossible.
Now,
so you can imagine.
Most of us at this point, thinking there is no experiment that will ever prove this, would think there's a sort of failure coming down the line at me. Your book is very much about embracing failure.
Yeah, that's right.
The beauty of falling.
That's right. There's a level of reinventing ourselves. Often people ask me, what are you thinking about? What is the next question? And really trying to phrase our challenges in a question that I can answer. That's most of my job. Most of the time I don't even know how to do it. But there's a high level of creativity and understanding how we can push ourselves at this point of failures. And actually, if you rephrase the question after that, you can, in principle, detect the quantum nature of gravity if you use the whole universe as a way to do that. And we know that at the very beginning of the universe, or we think at the very beginning of the universe, there were some quantum fluctuations that we may be able to observe today, using the universe as a way to stretch them and then observe them today. So we really need to play with what is at our disposal to do that.
Lisa Gartner, you wanted to
And so what Claudia was hinting at or stating out, right, what's great is like science at the forefront of discovery needs to be creative. It needs to be allowed to make mistakes. And I think a lot of times science is still thought of as this really rigid structure with old ideas and cobwebs on it. It's really not what we find, because you have to have educated best guesses, lots of creativity, and you have to bring people back together, because luckily we live in a time where not one person can know all of science anymore. And so I think what you get here, and this is also where it pertains to education, you know, we have to rethink the way we present science too. And for example, I just flew in yesterday from the US. It's an amazing way to travel and meet interesting people too.
Mark Fromhold, that is your cue, because you're very interested in how physics is taught. I can't imagine any kind of curious 15-year-old listening to what we've just listened to being bored. But obviously there's a question about how much, as it were, not knowing you can put into a syllabus. What are your concerns about how we teach physics at the moment?
Yeah, I mean, if you look at the GCSE syllabus at the moment, it's broadly similar to when I did GCSE physics quite a long time ago, and actually broadly similar to Victorian children